Okay, hello Ukraine. Good morning. Not so many people so far. I know it's really hard to wake up on a Sunday morning, but anyway, I'm really grateful that you actually find some time to come here. Okay, my topic is deep generative models for audio synthesis. And today you will learn how we can actually synthesize audio using deep learning. I will introduce you into the concepts developed by such companies as Google, OpenAI, DeepMind to create the best artificial audio ever existed. I want you to know that this topic is really wide, and there are a lot of things that I would like to share with you. But we have only 40 minutes, so I have to be really concise. But for those who would be interested in diving deeper into the world of speech synthesis, I prepared really nice collections of links and resources on the last slide of my presentation. Okay, let's proceed. At first, I want you to look on the screen and notice this strange-looking thing on the bottom of the slide. The thing is called a waveform, and that's how raw audio looks being stored in a digital format. On the y-axis, we have amplitude, and on the x-axis, we have time. And when you hear sound from the speakers, that's because they vibrate according to these amplitude values and create an acoustic wave our ears perceive as sound. And today, I will talk how we can actually apply machine learning to synthesize such naturally sounding artificial waveforms. Okay, to give you some context, here's my background. Currently, I work for ReSpeecher. It's a startup where we do voice conversion, a technology that allows you to speak in the voice of another person. Currently, we work mostly with the movie industry, audiobooks, and games. And a typical pipeline for a voice conversion system looks like this. On input, we have our source speaker waveform. It could be you or me. Then we extract some features using some signal processing methods like Fourier transform. We throw these features into the encoder, which is typically some deep neural network. This step basically is what you can see in a typical speech recognition pipeline, and we typically don't have any serious problems doing this. But then some black magic happens. This is really specific to voice conversion, and it's black magic after all. So I will not talk about this today much, but this third step is actually why I'm here. Here we have some encodings from our encoder, seasoned with some black magic. And now we want to convert these encodings back into the waveform space. But now it should be a waveform of our target speaker, which could be some actor or maybe celebrity. Despite this step looks really simple, really similar to what we see in the encoder part, only kind of flipped, it appears to be much harder to do in practice. And on the high level, it doesn't really matter whether we want to use speech synthesis as a part of a voice conversion system or for something else like text-to-speech. And today I decided to focus mostly on text-to-speech application, and the reason is that I find this approach to be more accessible for the broad audience, and also I believe that almost every one of you, or even every one of you, have ever used text-to-speech either for fun or maybe to learn how to pronounce a rare word. This is one of the technologies big tech companies such as Google, Amazon, Microsoft, Facebook invest a lot of time and resources in hope to use it for their public APIs or maybe for their voice assistants such as Cortana, Alexa, or Siri. So the task itself sounds really simple. We have some text and we want to synthesize the corresponding audio waveform that we could then listen. And there are several reasons why I actually claim the task is hard. The first reason is that a typical waveform has a very high dimensionality. Modern recorders use sample rates, meaning the number of amplitudes per second. With amplitudes in this context also sometimes called samples. And the sample rate ranges from 16,000 to 44,000 samples per second. And that's a lot because we have to model all these values as a whole. And you can see that even 1 second of audio can contain all sorts of variations. We see some periodic signals, aperiodic signals, silence, and noise. Another reason is that if we kind of zoom in, we see that all these values are really correlated. So they cannot be modeled as an independent random variables and should rather be modeled jointly, such as each value kind of knows what are the values of the other amplitudes. And you know, this signal exhibits some periodic pattern, and we should also somehow handle this. And the last reason, but maybe not the least, is that the same text can in fact be articulated in a myriad of different ways. For instance, the same text can be spoken very fast, very slow. It could be spoken very emotionally, maybe really quiet. And you know, people can speak with different accents. And a good speech synthesis system should be able to capture all these variations and have some instruments to allow us to tweak the way a particular text is spoken. And here I want you to know that there are a lot of, I would say, conventional approaches that rely heavily on domain knowledge that actually do speech synthesis. And they're great. They are simple. They are sometimes really easy to implement. We understand how they work really good, but they have their drawbacks. For instance, it's really hard to control prosody, which is an emotional content with these methods. Next, sometimes they require a lot of labeled data, and you know, getting labeled data is really hard and sometimes really expensive. They sometimes rely on very unexpressive models, such as hidden Markov models, which is fine in certain contexts, but sometimes these models fail to actually capture the global structure on our signal. And probably the last reason is that these methods rely heavily on domain knowledge, and this could be an advantage if you spend 5 years probably learning all the signal processing stuff and other tricky things. But if you just want to get a nice result, this would be a problem. And what is really embarrassing is that even if you are a domain expert, these methods still often sound not really good. They sound robotic, they sound really noisy, and it's not like real clear what we have to do to these methods to make them sound better. So even these methods don't work really great for domain experts. What could we do? Well, my talk is called Raw Generative, Deep Generative Models for Audio Synthesis. So you might expect that we have to use deep learning, and that's right. But at first, we have to reformulate our task. And we will reformulate our task as a joint probability function or density for continuous values estimation. And the idea is that we want our model to actually learn which combinations of amplitude values are likely to correspond to a given text. As we already know, there could be like multiple versions of waveform that correspond to the same text. And this process is really similar to what we can see in a typical natural language translation framework, where we have this kind of model that actually learns the dependency between two languages. So we have, for instance, English language as our source language. We have German as our target language. And we want our model to learn basically two things. The first thing is that we want our model to learn the dependency between words of our source language and the corresponding words of our target language. But the second thing is that our target language has something which we call a language model, which is basically a set of rules that define which words are likely to appear in the same context and which are not. And we can apply the same idea for text-to-speech or other synthesis problem. We also have some text waveform pairs, and we will have some model, probably a neural model, that we want to learn this dependency. And it's really common to use something called maximum likelihood estimation to find the parameters of such networks. Here is a really quick reminder of what is the maximum likelihood principle. So suppose we have some data, some two-dimensional data that in this case looks like it's normally distributed. So probably we want to fit a Gaussian probability density function to this data. And according to the maximum likelihood principle, what we have to do is basically to maximize the probability of observing this data with respect to the parameters of the distribution. And for the Gaussian case, it leads to a very expected result. For instance, for this parameter mu, which is basically a location, we get that this mu is basically an average of our samples. And we can apply the same principle to any other densities, which are much more complex. And in fact, this is just an example, and we probably cannot use a simple Gaussian density for our waveform modeling case, because it turns out that it has a lot higher dimensionality and probably has much complex structure. So we have to go for something else. And one model that people use a lot for such problems is called autoregression. Here I want to ask you, how many of you have ever worked with time series forecasting? Please raise your hand. Oh, that's a lot. And maybe sometimes you worked with language modeling using recurrent neural networks. It's a very, I would say, common task for different deep learning classes. Okay, anyway, the idea is really simple. Here we assume that our target variable, our waveform, can be treated as a sequence, and we assume that each next value can be represented as a function of the previous values. And this makes our amplitude values to be kind of aware one of each other, and still keeps the computation to be tractable. And one of the most famous models for speech synthesis that actually uses this principle is WaveNet. This paper came out in 2016, and it was a real breakthrough. The authors demonstrated it's possible to use pure deep learning model to actually outperform all previous attempts based on either concatenative methods or parametric methods, the two most popular methods before deep learning era. And what is really nice is that the WaveNet structure is really simple. It's just a stack of convolutions with a special form of padding to simulate this causality effect. Recall that for an autoregressive model, it can only have access to the previous values, but not on the future ones. And what you see on this slide is how actually WaveNet generates samples. It takes the previous amplitudes along with text as a condition and outputs a distribution over what could be the possible value for the next amplitude. And to train a WaveNet, all we have to do, according to the maximum likelihood principle, is to maximize the probability that WaveNet assigns to the current waveform given the corresponding text. And since our model is autoregressive, all we have to do is to maximize individual one-dimensional probabilities on each time step. So for instance, we maximize the probability of observing the second sample given the first, the probability of observing the third given the second and the first, and so on and so forth for each amplitude in our waveform. And what is really nice about convolutions is that they can be computed in parallel. So we can do this very fast for all time steps in one step. But the generation process is nothing like that. Here we have to do sequentially, like on this slide, and wait for our WaveNet to sequentially process our waveform sample by sample. And this is a problem. Well, here is a very, I would say, well-known meme. And here is my adaptation. So the problem is that a typical WaveNet, even on modern hardware, can take something like 20 minutes to generate even a single second of audio. And of course, we cannot use this model if we want to use speech synthesis as a part of our real-time pipeline. It works really great, but takes a lot of time to generate audio. So if we want to actually use speech synthesis in real time, we probably want something else. And what you see on this slide is called an autoencoder. The concept of autoencoders is really old. People use them a lot in the past for different sorts of tasks, such as feature extraction and anomaly detection. And a typical autoencoder has these two parts, the encoder and the decoder. And the goal of the encoder is to take an original data point, which is in our case is a waveform, and produce a compressed high-level representation of this data point. And the decoder's goal is to take this compressed representation and try to kind of reconstruct the original input. And by training these two parts jointly, we hope that this intermediate layer, also called a bottleneck, would learn some useful properties, some useful representation of our data that we can later use for some downstream tasks, such as classification. And it turns out that we can actually modify this classical autoencoder to do the probability estimation task. One approach is called Variational Autoencoder, and here we now we say that our encoder and the decoder both represent some probability functions rather than some deterministic functions. So for instance, our encoder estimates what could be the possible values of our bottleneck space. In this context, it's also called a latent space. And the decoder estimates what could be the possible values of our waveform given this latent vector. And we can actually show that this process of learning these two parts jointly with a certain form of loss function is basically an approximation to learning the actual data distribution, exactly what we want. And now we want to sample a waveform from a trained variational autoencoder. And what we have to do is we first sample from our latent space, which typically assume to have really simple distributions such as Gaussian. Then we combine this sampled Z code with some text and pass this two guys into the decoder, which basically is some deep neural network, and it kind of reconstructs the waveform. And our hope is that if our autoencoder has been properly trained, this should be a natural sound in waveform. And a very good thing about autoencoders is that this latent space often learns very useful, very high-level representations of our data. In our audio case, sometimes it happens that some components of that vector actually correspond to prosody, which is an emotional content. Some of them correspond to tempo, some of them could correspond to accent, and much more. And by tweaking these values, by interpolating in this latent space, we can actually control on how this audio would be actually generated. For instance, we could want to make our audio to sound happy or sad or something else. But unfortunately, this formulation of variational autoencoder very often leads to really blurred and distorted samples. The reason behind this is not really clear, and this is an active area of research. But here exists an upgrade. It's called vector quantized variational autoencoder, and the idea is that we keep our structure to be basically the same. What we change is that we say that our latent space is now a discrete space, and a distribution over this latent discrete codes is now modeled by some autoregressive model. And it can be shown that this model actually works really well for on a wide range of tasks, starting from some image problems and even to reinforcement learning. And it's also possible to generate really nicely sounding audio with this approach. Okay, the last approach for today is called normalizing flows. The idea is really similar to what we have seen in the variational autoencoder case. We also take some simple random variable z with some known distribution, such as Gaussian, and we apply some transformation to this variable to make it a bit more complex. So for instance, in this case, our transformation is matrix multiplication, and after we have applied this matrix multiplication to our Gaussian data, it became a bit more complex. On input, we had this spherical Gaussian with diagonal covariance matrix, and there we can see that it now has some non-diagonal covariance. But what is different from a variational autoencoder case is that now we constrain all these transformations to be invertible, meaning that given some input, we can always compute the output and vice versa. And we need this property to be able to use something called the change of variables rule, which has some theorem from probability theory that defines how we can actually change the probability density function after transforming our base variable z with some transformation. And it's really simple. All we have to do is to take our original probability function, substitute our new variable in terms of old variable, and multiply it by a scalar value defined by the derivative of our transformation. And I know that might sound a bit complicated, and here is an example, a really simple one-dimensional example. What we have on input, we have this what people call standard normal distribution with zero mean and unit variance. And here we want to apply some linear mapping to this base variable z, such that y is z times sigma plus mu. And using the change of variables rule, after computing the derivative, which is basically just a scalar derivative in this case, and substituting this old variable in terms of a new variable, we actually get a very well-known expression for a general case of one-dimensional Gaussian density. And that's really nice. So we started from a really simple distribution and used some transform. We know how to compute the inverse transform. We know how to compute this derivative, and we got something more complicated. But again, this is just an example, and in practice, we could use basically any transforms, any nonlinear transforms, as long as they are invertible. And moreover, we could stack multiple transforms in a chain, forming something people call a flow, so that on input, we have our Gaussian variable z0, which we sequentially transform with different functions. And on output, we have this zk, which we would assume to be an approximation to our target variable. And of course, we could extend this change variables rule to work for this multi-transform case by just repeatedly applying it to this chain. And again, this is just a density, so we could apply our old friends, the maximum likelihood principle, to actually learn the data distribution with this transformation. Okay, and now is actually how people use this approach for doing speech synthesis. Okay, I hope you remember WaveNet, which is an autoregressive model. It has this very bad property of being really slow on inference time, because we had to feed these values one by one, and so on and so forth. But now it turns out that we can, at least we can try to kind of express this model as a normalizing flow. And this particular approach is called inverse of the regressive flow. And the idea is that we want to keep the same structure, the same WaveNet structure with all these convolutions. But now the difference is that we condition this WaveNet not on the previous amplitudes, but rather on these latent codes. So you see, in this case, we had our one-dimensional distribution over the next amplitude. It was a function of the previous amplitude. But in this case, it's different. It takes these latent variables as an input. And why it's different? And the difference, and what is different is that unlike these amplitude values, these latent variables, being just Gaussian variables, can be sampled in parallel, just like a big Gaussian vector, also known as white noise in signal processing. And then we can use this property of convolutions that they can work in parallel, so we can apply them and actually get our waveform on output. But, as it always happens, this approach also has its drawback. It turns out that to actually train this model, we need to use the same sequential process we use for our standard WaveNet on the generation time. It basically means that although we can sample very efficiently, very fast, we cannot train this model in a reasonable amount of time. So what we can do? Well, it seems that some people from DeepMind actually have an answer. What they did is called parallel WaveNet. And the idea is really simple. What we do here is that we take our old autoregressive WaveNet. On this point, it has been already trained, so it learns our data distribution really well. And what we know about this WaveNet is that its inference is really slow, but it does probability estimation really fast, and also it trains fast. So we could train it, and then we take our new WaveNet that has this kind of inverse property. It does very fast generation, but has this slow training. And what we do here, we want our original WaveNet, in this context, it's also called the teacher. We want it to kind of teach our new WaveNet, which is called the student, by kind of looking on samples that this student model generates. So we train these two models jointly, keeping this old WaveNet being frozen. And we sample a bunch of waveforms with our new student WaveNet. And then we use this old autoregressive WaveNet to kind of estimate how good these waveforms are and if they really correspond to a given text. And so basically what we are doing here, we are using this teacher WaveNet as a loss function for our student WaveNet. And this process can be really similar to what you could see in such approach as generative adversarial networks. But the difference is that while in a generative adversarial network, we have these two models, a discriminator and a generator, and we train both of them. Here we keep this teacher model frozen. We just use it as a pre-trained function, and we use its estimates as our loss function. And after our WaveNet student has been trained, we can basically sample waveforms from it. And we expect if it really learned well from the teacher, to be able to generate actually the same good sounding audio. And that's the idea. By the way, this approach is called probability distillation, and it's used really widely in different areas of machine learning, such as computer vision, to, for instance, distill a very big model into a smaller one. And this is actually one of the approaches such companies as Google use for their production pipelines. There are others, but this one, I would say, is probably the most common one. OK, as a conclusion, I can say that now, unlike to maybe 5 years ago, we have a lot of methods we could actually use for speech synthesis. And some of them are really great. For instance, a typical audio waveform sampled from a WaveNet or from this parallel WaveNet actually sounds really great and almost indistinguishable from the real audio. And which model to use actually depends on your application. If you want to work in real time, obviously you cannot use an autoregressive model such as WaveNet. You have to use something else, such as autoencoder-based approach, or probably this parallel WaveNet approach. But it seems that these two methods, both Variational Autoencoder-based approach and this parallel WaveNet-based approach, are really tricky to train. So probably, if you just don't care about the speed, it would be much easier for you to use WaveNet. OK, it seems that that's all. Here are the promised slide with a lot of different links. And I'm really eager to hear your questions.
And Dmitry, we have a few questions for you, OK? One second.
Yeah, thank you for this question. Well, it seems that using Ganz is really now a standard for different image generation tasks. I guess all of you have seen all these style Ganz samples and all this various, this phase doesn't exist and so on websites. And all these approaches actually use some form of GAN, a generative adversarial network. But it turns out that applying GANs for speech synthesis tasks is really tricky. And the reason is that apparently this GANs, they model the global structure of our signal really well, but they kind of miss some very subtle, very minor details of our audio. And for our eyes, it's not really important to have all these very low level, very minor details. But for our ears, it's really important for our signal to be really properly modeled. And for some reason, GANs actually struggle doing this. And what I see now is that there are a lot of ongoing research on actually applying GANs to speech synthesis. But currently, I can't say that any GAN-based model actually outperforms one of those I mentioned throughout this talk. Well, it actually depends on your model. But it turns out that currently they are really resource hungry. And probably you would need much more to train this normalizing flow that, for instance, to train a GAN-based model or probably this variational autoencoder-based model. But also, I see a lot of research, and very large part of this research actually addresses the problem of this normalizing flow training and in reducing the amount of hardware needed to train a flow-based model. The process is actually the same as for a regular variational autoencoder. We just sample from this bottleneck space, but now our distribution is modeled from this by this autoregressive model. So we first sample from this autoregressive model, we get our latent code, and then we basically throw this code into the decoder, which is responsible for generating an actual waveform. For a typical text-to-speech model, we need something like 20 hours of data. And there are a lot of data sets that can be found across the internet. But the problem is it seems that you can't use like any data. These big companies, such as Google, they actually use very carefully prepared data sets with really nice balance of different words and phonemes. But even with a non-balanced data set, you could still train a good text-to-speech model. So yeah, so you could just Google text-to-speech data sets, and there would be plenty of them. Yeah, there's like even like the next level of variational autoencoder called variational vector quantized autoencoder version 2, and in fact it turns out to be really better than this previous model. But as far as I know, in this paper they tested it only on some image generation tasks, so it's hard to say if it's really better on some speech problems. So yeah, probably it's better, but it's really hard to say without looking on the samples. Sure, some approaches actually do this speech synthesis in kind of like two-stage. For instance, there is a model called thank you, Decatron, yeah. And it actually does this. It actually generates this spectrogram as a first stage, and then it generates a waveform conditioned on these spectrogram frames rather than being conditioned on text. Yeah, so it's really common. Well, for kind of like some tabular data sets with like not a lot of variables, it's more common to use more conventional density approximators such as Gaussian mixture models. But if your dimensionality is really high, like in our case, there are like thousands of random variables, it's really hard to say what is the real distribution. So that's the reason we use this neural network-based approaches that, at least theoretically, could learn any distribution. And as in other neural networks, we can use different regularizers to make it to be more robust and work well. So I don't think this question actually has an exact answer. You can just try and see how it works. The reason is that this change of variables rule is only defined for invertible transforms. You just cannot apply it if your transform is not invertible. That's the answer. I don't remember I actually said that I love Ganz. Well, it's just like a certain type of generative model, and I guess the applications could be basically anywhere where we actually need to synthesize something. For instance, there is a Kyiv-based startup called Reflect. Oh no, I guess it's their product. But anyway, they use this Ganz to swap faces. And as far as I know, they work a lot of also with the movie industry. For instance, they could offer a particular movie to change some faces when some particular actors are not available. In a very similar fashion we work. Yeah, so this one application, I guess I could name like a lot more, but you know, we don't have like much time. Yeah. Well, it seems that why not? I mean, if we need to generate some waveforms, we could use WaveNet. It's not. It's as we can see, it's used both in voice conversion. It's used in text-to-speech. So why not use it for some other task? Yeah, I guess it should work well. Yeah, we have some. Yeah, like training these sequence-to-sequence models is not really trivial in many cases, but there are a lot of good papers that actually use like different forms of attention mechanisms, and they have a lot of different tricks to make your training to be more stable. So it's like solvable. Yeah. Okay, I guess you will have access to my presentation, maybe like in a couple of days, so you could just follow these links.
That's all. Many thanks for Dmitry, please.